7. So that's at the point 2, -7. So there's my vertex point. I need another point to the right of it. I can use symmetry. I hadn't really talked about that in here, but notice it's going to be the same thing on both sides. So if it's at -5 when I go 2 to the left of my vertex point, it's also going to be at -5 when I go 2 to the right of the vertex point. So I should have a dot right here as well. Or you could just pick a point and plug it in. You could plug in 4. If you plug in 4, you get 4 minus 2, which is 2. 2 minus 7 is -5. So you see, you get the same thing. And remember, it's a V. So here's the two parts of our graph. The pink part is the first part. That was that quadratic. And the second part is an absolute value. And that's that V. And it looks like that. Would this be considered continuous? No, why not?
Because you had an open circle and you had to take your pencil off.
Do I still have an open circle?
Not anymore. But...
No. Because that open circle went away, it became like the very first one we did up here. That's what happened here. Either the line or the parabola probably originally had an open circle, but the closed circle always covers up the open circle. So it is actually continuous. The only two up here that aren't continuous are the second and the third one. So this is saying as x, that arrow, change color here, that little arrow, you read as approaches. So that's saying as x approaches 0, and that little minus sign means from the left. So as x approaches 0, so as I trace this line on the left side of 0, so as I trace it, as I get closer and closer to 0, what is my y getting closer and closer to? -5. Does it actually equal -5 on the pink equation? No. There was an open circle there. So what do you suppose this one's saying? As x approaches 0 from the right. That plus sign just means from the right. Awesome. As I approach it from the right, let me change colors. Here we go. So as I go from the right, that's this way. As I approach 0, what am I getting closer and closer to? Still -5. Okay, so we did that using the graph.
So the number doesn't change based on if it's an open or closed circle?
No, it does not change. Just because the closed circle covered up the open circle. And actually, even if it didn't cover it up, it's still approaching that number. Whether it actually reaches it, meh. But the approaches part, that's what that arrow means. It's getting closer and closer to. It might actually touch it. It might not. And that's okay. So we're going to do the same thing down here, only instead of looking at the graph, because we're not going to want to have to graph that every time. So instead of looking at the graph, we're going to use the equation. So as x approaches 0 from the left, q of x approaches and I would use the pink equation. Because up here, this pink equation, see how the x is to the left of 0? So that means that's the equation that goes to the left of 0. So q of x approaches that pink equation, which was negative x plus 3, so that'd be 0 plus 3 squared plus 4. Which is approaching negative 9 plus 4, which is indeed approaching that negative 5, like we said. So we could do that, figure it out without the picture. We just know if I'm to the left of that number, I use that top equation because x is to the left of 0. And x is less than 0 there. So that would be to the left. On the next one, as x approaches 0 from the right, q of x is going to be the other equation. The other equation is the absolute value one, yes, because this side, absolute value, it says x is greater than or equal to 0. So that means all those x's, everything would be to the right or bigger than 0. So if I'm approaching it from the right, then I have to use this green equation for the bottom equation. So that is absolute value of 0 minus 2 minus 7. 2 minus 7, which is negative 5. So since both pieces approach the same y value, of negative 5, and q of 0 is indeed negative 5, then q of x is continuous at x equals 0. Now that's just basically saying, since that closed circle is on top of the open circle, it's continuous. Which is like the first example that we drew. And you know we'll be doing plenty examples like we always do. So if that one's got you going, we'll do more. Okay, so if you look on the back of this, it's got kind of like a flow chart. We have two different kinds of discontinuities. We have what's called a jump discontinuity and a point discontinuity. The jump discontinuity is where those two pieces, they just don't connect. And the point is where two pieces connect, but it's at an open circle. Neither one of them are filled in. So, for our examples that we did at the very beginning, the first graph, second graph, and the third graph, Which one of those would be considered a jump discontinuity? The last one, the third graph, because there's a space in between one graph and the other. Excuse me.
So the point is, it's like an open circle and a closed circle, or is that the
Well, it doesn't matter. That's a good question. It doesn't matter if there is actually a closed circle in there or not, but they have to connect at an open circle like here. So this could be this with or without that point. Good question. So, we're going to look at these and we're going to figure out if they're jump or if they're point discontinuities based on their graphs. So for this first one, we've got this absolute value, f of x. Make it a little bit bigger. And we've got it going from -8 to 3. Notice how 3 is an open circle. And then at x is greater than 3, it changes. Now it's this line. So would that be point or jump discontinuity?
Jump.
Yeah, it's obviously a jump. And it's a jump because of that big jump. Whether they're open or closed circles, it does not matter. It's just you're jumping from one point to another. They're not connected, whether it's an open circle or not. Okay, what about the one below it? Point. Right here, they connect, but it's an open circle. So that makes it a point discontinuity. Okay. This isn't too bad, right? What about this one? This is jump. Because, again, there's that big jump between those two. Whether they're open or closed circles, they're not connected. And this one? Point. Because there's a point where they connect, but it's an open circle. This point doesn't matter if it's there or not. Now, it'll matter when you're listing domain, if you're listing that, but it does not matter at all whether it's a point or jump discontinuity. The fact that it's a point discontinuity is only because of that open circle. Question. All right. So now we're going to look at these graphs that we had over here, f of x, g of x, h of x, and p of x. And we're going to fill in this table. It's already what we wrote over there. We're just going to, kind of hone it in a little bit more, make sure we got it, all that good stuff. But the bell is getting ready to ring, isn't it? So I'm going to stop there. This is a great place to start tomorrow or Monday.